Vasily Bulatov from Lawrence Livermore National Lab. Vasily is a senior scientist there and also a distinguished member of the technical staff. He works in the general area of materials physics. He has made a number of contributions to the understanding of material strength and degradation, with particular emphasis on the role of microstructures. One thing you may not know about Vasily is that he spent 8 years at MIT. As a visiting scientist?
No, as a glorified postdoc, really. Right.
In mechanical engineering.
In mechanical engineering,
Yes.
right.
When I was a student there.
Yeah.
So today he's going to tell us about the role of exascale computing and how it has enabled large-scale molecular dynamic simulations for studying material dynamics.
Thank you so much. And it's great to be back. I spent 8 years at MIT, and that's where my kids grew up, around here. The campus changed a lot. I mean, I was visiting once in a while, but it's still a lot of changes. But I like the spirit is the same. It's really very proletarian, It's great. And I thank you very much, Nick, and for kindly inviting me. It's my pleasure and certainly my great honor to speak at this distinguished seminar. And because I always forget that, I start by naming some of my key collaborators. There were a lot more people actually involved into the work I'm going to describe. But these are some of the key people, some of them in the audience. Of course, I'd like to certainly acknowledge the funding support and, most importantly, the computing programs that were supplying us with cycles to run the simulations I'm going to describe. We run a lot more other simulations, not only the ones I'm going to show you, and in particular, Livermore Computing Grand Challenge program that has been continuously supporting us since 2008 up to now. And its director actually was here yesterday, but he had to leave to Livermore this morning, Eric Drager. So the way I got into that is that in the ASK program, Advanced Simulation Computing Program, was started about 1995. And we got a small grant from Lawrence Livermore to work on that with Sid Yip and Ali Argon, who were my mentors at MIT at the time. And then I worked on that for a while until they yanked me into Lawrence Livermore, and I stayed there since, for like 28 years now by now. And the point of this program is indeed to predict with confidence the behavior of nuclear weapons without ever needing to test them. And confidence is really a key word here. We need to know what our uncertainty and our predictions. So we paid really prime attention to uncertainty quantifications in our context. So my neck of the wood here is physics and engineering models. These are part of this large complex, simulations, and in particular, models of material strength and damage, how materials of relevance behave under extreme conditions of very high pressure, strain rates, temperature, and so on and so forth. So that's the context, okay? And it was realized early on, and I think, Christian, actually, you were from the very beginning of ASK program, the Lawrence Livermore. So tell me if it's wrong, but it was realized really very early that when it comes to metal strength and plasticity, you can build, by now, quite traditional hierarchy of methods, to multi-scale simulation capability, starting from electrons, atoms, up, and so on and so forth. But in this particular context, and you can pass parameters from bottom to up and so on. And if you do it right, then you can predict behavior of materials at the relevant scales of pieces, details, and the whole device and things like that. But when it comes to strength, it was realized that this is where there's a Russian proverb, a dog is buried, okay? So this is the critical, least understood link in this hierarchy, mesoscale, how dislocations behave in large numbers, in large quantities, and so on. And so collective dynamics of dislocation at this intermediate mesoscale was the weakest, least certain, but probably also potentially greatest payoff link in this hierarchy. And I would say that prior to our program starting in '95, the connection between dislocations, I'll tell you what they are in a second, and actual behavior of materials here was mostly motivational and or inspirational. I would say even now, to a large extent, but we thought to change that. And this is what the dislocations are. It has been realized more than a century ago that if you take a crystal and push on it, apply some mechanical force, it slides along certain crystallographic planes. Not any planes it can slide, but along certain ones. More than that, it slides also in those planes along certain crystallographic directions. And then it was some discrepancy between this theory predicting that materials should be that strong and how actually much weaker they were, until it was realized that this slip across the planes doesn't propagate at once, but in fact entails propagation of these line defects. There looks like a point here, right? This is the point, but in fact it is a line that propagates the slip along these planes. And therefore, why the metals or other crystals are much less strong than this theory would have predicted is because you don't really break all the bonds at once, as required in this picture. You basically break one at a time, okay? And these lines are dislocations. And the plasticity and strength of metals in most conditions of practical interest are grossly defined by dislocation motion, how they behave, right? So these are very important defects. And these days you can really watch them in any undergraduate lab, even that has a TM microscope, essentially. And but the point is, how do we get from individual dislocation behavior to predicting how much force it takes to break the specimen, okay, or destroy it in some other way, and so on. How you get from here to there? And it was kind of, again, and not until '91 when Gilles Canova and Ladislas Kubin proposed this discrete dislocation dynamics method in 3D, where it's basically what you do is just throw in dislocations in there, let them interact, move, feel mechanical force, and as a result of their collective motion, comes out prediction of what it will take to break this thing, right? All right, so the beauty of that was that nature itself tells you how you reduce degrees of freedom. Dislocations, just natural object, this is it. If you focus on dislocations and learn how they behave, you can forget about atoms. And in typical crystal, the fraction that highly distorted atoms surroundings in the crystal they take, it could be 10 to minus 8 fractions. So the saving of the degrees of freedom is huge. But this is how this dislocation dynamics method works, is that you learn how dislocations respond to forces they feel, including interaction forces between themselves, right? And how they behave when they collide. And you import this as in form of some sort of local rules into dislocation dynamics code, and then you evolve forward in time. Keep recomputing the forces and keep evolving and so on. And as a result, you can presumably compute some great things that people were arguing for ages why it is so, but they are certainly defined by dislocations, but we couldn't compute them, such as this kind of staged hardening with inflection, or a nature of intricate dislocation patterns that this is actually relatively simple, but there are others and so on, and various other things that are really fully understood that they are due to collective dislocation behavior. But how to compute was not quite available. And so this DDD method proposed in '91, three-dimensional, was the way to go for it. And there are two challenges generally for dislocation dynamics method. It kind of, again, became a darling of multi-scale modeling community, again, because of this beautiful reduction on degrees of freedom. And it's just very nice. And one challenge, of course, is fidelity. When you learn how dislocations behave on atomistic scale, atomistic time scale, length scale, so you don't want all this information to be lost in translation as a local rules to dislocation dynamic simulation. So that's important. The other one is computability. It's actually not a cheap thing. In fact, we have been major computing time hogs with dislocation dynamics simulation in Lawrence Livermore laboratory. The interactions are long range, so you need to compute them. That's expensive. Line motion is extremely intermittent. Most of them don't move most of the time. Sometimes they do. Dislocation intersections can be violent. You need to resolve them and so on. And so these are, the challenges. And one of the things was just an example of it. This is just a fairly famous, at least at the time, simulation by Farid Abraham, 100 million atoms, at which point was world record. Farid worked in a PR department in IBM Almaden. So he was basically PRing for IBM computing. And so he ran this beautiful simulation, and he was publishing this in computing journals and stuff. But then he said, look, there must be some interesting physics in there. So he almost locked me up in the room, gave me the VHS tape, and I spent a few hours watching, and there were actually quite a few interesting things to observe there. One of them, kind of an example shown here. Oh, that one? Okay. One of them is shown here. You see that two dislocations, they are the same type, but of different Burgess vectors, sort of come close together. They like to join. They join into a junction, 1, 2. But then a dislocation number 3 is lurking behind somewhere, and then it joins with 2 and begins to zip another junction, 2, 3. And by doing so, it unzips 1, 2. So it's a love triangle situation. It actually kicks out number 1 completely out of this partnership. Okay. We were pleased to see that properly parameterized dislocation dynamics simulation reproduce this behavior. So it that's how you sort of go about fidelity. Just make sure that atomistics and dislocation dynamics agree how they deal with situations like that. Okay. So, but now about computability. So at the time I joined the lab, there were codes, dislocation dynamics codes, but they were really only able to produce minuscule fraction of plastic strain required to actually compute plastic strength. We thought to change that, and of course, this is what we decided to engage. So in 2000, I started parallel dislocation simulation project, abbreviated Paradis. And the idea was to meaningfully engage multi-resolution and massive parallelism in computing, in evolving these dislocations, right? So in about a few years, it started to deliver the needed benchmark. It actually was able to compute strength, get a few percentage of strain, and so on. And was great. Management loved that. But it also turned out to be an interesting research tool. Late Maria Bartelt, actually looking into some of our dislocation dynamics simulations, observed something we couldn't quite understand right away. Typically, dislocation network, when they collide, they zip into junctions. I showed you one example on the previous slide. And there are 3 nodes that they form. And these are like basic element of this dislocation network. But she observed 4 nodes. And we couldn't quite understand what they are. But then we figured out, this is what happens. 1 and 2 join into a junction, and then the third dislocation, not of the same kind of 1 or 2, but with different Burgess vector, can be attracted to that already existing junction and join additionally. And as a result, at the end of it, you get a quadruple node. Okay, and then we thought, what are the conditions in which formation of these quadruple nodes are more likely? So we designed an experiment, ran the experiment, deformation experiment, thinned this into TM transparent films. And I was bringing pizza to our TM microscopist, and he actually found that out of 35 suspicious configurations, suspicious for the presence of such 4 nodes, a good fraction, about 30%, were correct quadruple nodes. And they have very specific signature in TEM contrast. So we identified that these are there. It was very pleasing. You get something from simulation or theory, and you predict it, and it is there. So it was not just sort of computational engine. It was also a research tool. So it was very pleasing. And we then observed something also quite interesting. Again, I said that most of the elements of this network are 3 nodes. There are occasional 4 nodes. But for some reason, we almost never seen 5 or 6 nodes. So why is that? So we kept looking, and later on to prove the theorem is that it's actually a fundamental property of the dimensional space. is that only 3 nodes and 4 nodes can be mechanically stable. 5 nodes and 6 cannot be. We do observe them very occasionally, but most of the time they're not there, okay? And it just has to do with that. So basically, and more than that, among the 3 nodes and 4 nodes that can be stable, the 4 nodes are by far stronger holders of dislocations in place. Okay, so that's a sort of later story. These are the ones, yeah. Okay, so we then continued with Paradis, but then recently established a, Paradis was released under limited license. Now we have MIT license for a new project, OpenDIS, and we had held a couple of workshops, very well attended, close to 200 people in one of them. And that's what we call OpenDIS. Essentially, this is a manifesto. It's intended as a sort of community development platform for dislocation dynamics method. And it's kind of logically consists of 2 pieces. One of them is the mostly weight size group at Stanford. This is like writing prototypes, functions, and also drivers in Python. This is very easy to do, and you don't even write this thing because chatbots do it for you. But something that proves to work well, Nicola Burton at Lawrence Livermore actually goes ahead and re-optimizes it, writes it C++ very efficiently and under Cocos to run efficiently on GPUs. And the only difference between function here in Python and here in Cocos is basically just 1 letter. It's E added to the function name. So that's it. So that's about it. Now it's actually what I wanted to mostly talk about. So we had lots of fun with this mesoscopic methods, and indeed, it's just great fun. And in part, our interest was forced interest because we couldn't afford to run simulations long and large enough to actually capture all this collective behavior dislocations in DirectMD. We couldn't for a while, but I was kind of watching this curve for myself. What this is that it's a log plot, decimal log plot of theoretical peak performance of the world's fastest supercomputer. As a function of years, starting from 1993, this list is compiled of top 500 computers twice a year in June and November. So this is the fastest. The flat regions, you see that this computer stayed fastest for 4 such periods. Okay, that's basically, this one is 6, right? The top one, by the way, is our El Capitan, currently the fastest machine. It's already like 3 periods fastest. And, this is interesting. So it basically goes with some Moore's law. And we thought, okay, why don't we try what was not possible before? Maybe it is possible now. So it's about 2015. We started probing the waters with DirectMD simulations of this sort of crystal strength with all atoms and so on. This is really the reason, is that since 1991, when dislocation dynamics method was proposed, the peak flop rate increased by 8 orders of magnitude. 1991 is here somewhere, so there's no 500 list back then. 8 orders of magnitude. Total computing capacity, how many flops you can generate in a year, is 10 zeta flops. Okay, so we're into zeta stuff. By the way, most of it is in your phones. So, right. And now, most impressive was the reduction in the cost of computing. Right? The 63 and 93 are obviously an estimate, but this is a real number from 2023. It's, I think, 13 orders of magnitude reduction in the gigaflop. It's quite amazing. So we could try to do something, hopefully, which we couldn't afford to do before. And that's what we embarked on doing. This is what I also want to show, usually show it later on, but this line is the lowest, 500th fastest supercomputer on the 500 top 500 list, okay? The reason I like to show it is because it kind of says that, look, on average, it takes 6 years for the world's fastest supercomputer to become 500 is fastest. Okay. And therefore, what's available to a few computing centers like Lawrence Livermore and others will become commonplace pretty much in 6 years. Unfortunately, it's growing. I don't know what's behind it. I just show it to you, right? By the way, if you have questions along the way, absolutely feel free to interrupt. I am totally fine with that. I will not finish everything anyway, so I'll have to cut it somewhere. So yeah, this is where, but of course we are always at Livermore. We're always on this line, so we could try, and we did. So essentially, the idea was just completely sweep over around this mesoscale dislocation dynamics. And this is a movie made by Alex Stokowski. This is the only time you will see atoms. This is just illustrates how his beautiful dislocation extraction algorithm works. You just select some of the atoms that are defective, delete all the rest of them, cover these defective atoms with some meshes, and based on walking around these meshes, you can actually compute what is the topological charge inside each of these sort of tubes. And this is the Burgess factor. So it's a beautiful method, and it's quantitative. Not only it finds where defects are, it fully characterizes what this given defect is, right? Then you can use all kinds of things to visualize it, to please, to make it visually pleasing and so on and so forth. But basically that's the method, and that's the only thing you are going to be seeing. So all the simulations I'm going to show you are full atomistic, but you will not see atoms. You will only see dislocations. Okay. So 2015 we started to do that. And at this point, we're sort of running simulations at in the range of deformation rates, high rates, admittedly, from 10 to 4 to 10 to 9 per second. Above 10 to 9, all hell breaks loose. So we know. But model sizes can range from a few million to over a trillion by now. And again, these simulations of that magnitude were unthinkable previously, but they are becoming quite routine, certainly in Lawrence Livermore. And you can sort of see how these dislocations behave, how they move. This is a static picture, but you can look at the structure of this network, what it consists of. So a lot of information you can glean into when you run the simulation and analyze them and so on. So one of the things we, that first paper, when we published, was interesting is that we did, impose all kinds of complex deformation trajectories, histories on our virtual specimens. Interesting is that if you keep eventually the same deformation conditions long enough, then the system asymptotically approaches a steady flow state, regardless where you started and regardless what it was in between before you actually started to hold it steady, it reaches the same steady state. That was amusing. It was not only flows stress was becoming steady, but all measures of dislocation microstructures, such as dislocation density, line geometry, topology of the network, are statistically stationary in these flow states. That was quite interesting. And that was a sort of funny simulation we undertook to illustrate it even further. We take a brick-shaped specimen, we deform it along one dimension, and then it becomes elongated along the other one. We push it this way. We essentially knead the metal, and we can do it indefinitely. I only show 4 cycles of kneading here, but we have done a lot more. So it's really stationary. It's quite amusing. Okay, and so we published this. And I think that was the most interesting implication, this kind of, I call it dynamic equation of state, is that under stationary straining, indeed, there is a asymptotic state of flow state where things are really become stationary. So it is a prime object for non-equilibrium statistical thermodynamics, I think. It's quite amusing, in some ways. We were not the first ones to hypothesize it. We just kind of nail it. It is there. Okay, so and then we continue to this sort of almost nostalgic goals of dislocation dynamics, by which time dislocation dynamics didn't deliver. What we thought, why don't we try with atomistics? So this is stage hardening, this is patterning, this is still work in progress, but this we have done. And what you see is a classical experiment by Takeuchi. What he did was a bunch of single crystals, oriented differently with respect to the tensile axis. Okay, so what orientation is expressed in the Miller indices, and these different Miller indices next to the curves show you the different orientations. And some of them show this inflection hardening, some show very simple parabolic. We then just run simulations of the same 7 single crystals at much higher straining rates, actually 10 orders of magnitude higher. But if you tell me that these 2 curves look similar accidentally, think again. I mean, it cannot be accidental. So essentially all the ordering and shapes of the lines are 1-to-1, okay? So, and then we continue to see what is behind when this thing first hardens slow, then faster, and then slow again, so-called staged or 3-stage hardening. And it turned out to be very simple, I'd say, embarrassingly simple. When a crystal rotates under tensile loading, you see this hardening. When it doesn't, and some orientations do not rotate, you see simple parabolic hardening, leveling off like that. We tried a lot more different crystal orientations, and it's always like that. So essentially, staged hardening, these 3 stages, is nothing but crystal rotation, okay? So there are a couple of examples. This particular orientation of a crystal, we compress it, okay? No, we pull it actually. It's such that it doesn't rotate. And you can see that the axis, its orientation axis, remains very much aligned with the tensile axis. These precessions are within a fraction of 1 degree, so it basically stays around the same. So it's stable, it doesn't rotate. Look at the curve. Next. This one starts here. This is axis orientation. I don't need magnification anymore to show what happens to the axis rotation specimen axis. It actually rotates visibly by quite many degrees. Look at this curve. So the crystal rotates. There's 3-stage hardening. It's pretty much what was expected. So I wouldn't necessarily share this sentiment of great physicist Alan Cottrell, who sort of opined that strain hardening is perhaps even more complicated problem to solve than turbulence, but that's what his opinion was. And that, in any case, whether it's hard or not, it really instigated thousands of papers, fierce fighting about different methods, sometimes really contradicting each other in terms of their assumptions. And it is pretty much it. The crystal rotates, you will have this hardening. So I think we more or less close the debate. Need to watch time. Okay, I'm doing okay. So, right. So, and this is what sort of on my table right now. I'm very interested in this asymptotic states of stationary flow. Again, to restate what we observe is that if you hold your specimen, single crystal, long enough, in the limit of the unchanged deformation conditions, in the limit of infinite time, you reach asymptotically this steady flow state. If it needs to rotate to reach it, it will first rotate and then become asymptotically flowing in that stationary state. The stationary state is not only, flow stress is stationary, but also rotation becomes stable. So, and it turns out there are only a few asymptotic stable attractor in the orientation space that exists, and everything is streams to them, okay? And that's most amusing. It's actually not me who figured that out first. It was Kumar and Dawson in the early 90s. But it turns out that within reasonable, plausible approximation or assumptions, you can reduce a very complicated 5-dimensional space of deviatoric stress. And that's how usually crystal plasticity is defined in that particular space of deviatoric stress, for example. You can reduce it to just one single scalar parameter. And that parameter alone enumerates the whole multitude of these 5-dimensional straining geometries. Quite amusing. I need to jump in. So this is actually Rodriguez space representation of SO3. And what you see is that parameter at that instant in the beginning of this movie, it's going to be a movie. It's equal to 1. And the way we define it doesn't matter how we define it. It's actually ranges between 1.0 to minus 0.5. And all this, as it slides, it's going to slide down from 1 to minus 0.5. It samples all kinds of deformation geometries, including the famous uniaxial compression, plane strain, and pure shear, uniaxial tension, and anything in between. So you will see this will slide down, and you will see how stationary points, the blue points, are in fact the stable attractor orientations to which things should stream. How they change. So first thing that happens is that they kind of break into discrete points. They were like rods first. And then at some point they begin to converge. They can merge, and some others can resplit. So things change really, all right? And then you get down to that, and there are different orientation of the so-called orientation fibers. So it just comes naturally. This was computed, simulated with some run-of-the-mill crystal plasticity model. So, but actually these behaviors, we checked it with various other models, it's pretty universal. Much of this behavior is actually symmetry related. That particular one was FCC. Okay, so going back, sorry, one slide. This concept of asymptotic plasticity and ability to reduce complexity to just one parameter and the whole flow to streaming towards stationary points, stationary states, can be potentially very constructive. I'm working on it right now. It leads to pretty concise quantification and quantitative description of crystal plasticity in general, but also potentially of polycrystal textures, where you hear horrible names of them, gold texture or copper texture. So there are actually some configurations of this asymptotic attractors, right? And it's actually fruitful ground to develop a statistical thematic approach to describing this sort of stationary flows, where instead of actually working as statistical thermodynamic does in the ensemble of microstates, you should be working on ensemble of micropaths. And when things are stationary, you are in a stable attractor, and then things are held long enough, you have an additional parameter, such as, for example, flow stress itself or deformation rate, that can serve as a thermodynamic constraint. So all you need to do is to maximize entropy over path ensemble with these particular constraints and this additional thermodynamic variable. So that's what I'm working on right now. And hopefully I can derive the equation of flow state somehow, but we'll see. Anyway, right. So yeah, it actually can be useful even for non-stationary plasticity. So as I said, as a function of P, this picture changes. This is only schematics. Where these things are, sources and so on, it kind of shifts. You've seen that on the movie. And if you're not stationary, you're only streaming towards one of them. While you're streaming, actually P changes. Well, you have a moving target, but you can always tabulate what are the streamlines in this orientation space. So you can always continue along the new streamlines. So I think it can be actually quantitatively very useful approach. To some extent, alternative to the classical crystal plasticity approaches that exist at this point. Okay, we kind of go ahead and we now become very interested in polycrystal plasticity. So, there is a famous whole page effect is that if the grains are smaller, then the polycrystal tends to be stronger. Okay, and you in the movie you can see that this is how grain coarsening happens, thermal coarsening in particular. This is a post-Monte Carlo simulation by actually with 200 billion spins actually by Thomas Applestrop. But it coarsens, and as a result of coarsening, it increases the grain size. So presumably that is weaker. This is stronger, and this is weaker because the grains are larger. So we wanted to look into that, in particular because there's some interesting controversies still exist in this field of polycrystal, nanocrystal plasticity and strength. In particular, I mean, Sid Yip, who many of you know, coined this term, the strongest size. And what it pertains to is that as you keep refining the grains, it becomes stronger and stronger until at some point it no longer does it. At about average grain diameter of 20 nanometers, After that, if you refine further, it becomes weaker. And that's what Sidibe said. That's the strongest side. This is 20 nanometers. Okay. Some people question it, that this is actually real, this sort of turnover to inverse Hall pitch effect from direct to inverse. But there was also a paper published a few 10 years ago or something, which shows that there is no Hall pitch strengthening at high strain rate deformation, which is very relevant for the kind of research I do. So in order to see, to sort out these interesting observations, not kind of reconciled yet, we engaged into very large simulations now, where rather than one single crystal, you have a bunch of them organized as grains. And again, in the same range of 10 to 4, 10 to 9, and containing up to and over 1 trillion atoms. Because when you do that, you basically span the entire range of relevant grain sizes from 2 nanometers, tiny, tiny grains, to 1 micron, where all these effects should completely disappear. It's basically macroscopic. And by the way, 1 trillion atoms can allow you, so there are some very preliminary results here, is that we actually see some crossovers in the behavior. At least these are, very preliminary result, remains to be formally sort of quantified, that there are 2 kinds of behaviors there. There is a rate-independent strength, but it depends on size. And there is another kind of behavior where it is rate-dependent, size-independent, or rate-independent, size-dependent. And there is a crossover line in the space of rates and size, grain sizes. So we're trying to now quantify this line where it is for a particular model of tantalum that we're looking at. So this is pretty huge simulations we're running right now. Riddle is involved into this work. Right. And so this brings me to some of other things I want to discuss. We call this very large simulations X-scale. It relates to exascale or cross-scale or whatnot. But essentially, these are in the domain we're running them and we're interested in. These are just huge, right? But they're also, statistically representative of complex behaviors that we're going after. So, but yet it resolves every tiniest detail. So it is simultaneously also a perfect computational microscope. You can look at every detail you care for. You can see every wiggle of stress strain curve, what is underneath, what's happening at that time, what causes it, and so on. Interesting that this is actual size of a simulation sample for in situ testing on the microscope, right? And these things need to be electron transparent, so it's like 100 or 150 nanometers thickness. That actually takes 1 trillion. So we can simulate a visible object with 1 trillion atom simulation right now. Okay. So that's the question. When and where such simulations are worth performing? Of course, you have to be able to afford them. And when your computational budget equals or rivals that of Germany, for example, you're tempted to use it. Okay, so that's my honest first take on why we run this simulation. But it's not only one take. What are they good for? What really deserves simulation of that scale? So let me lament in a few slides what it really happens. So going back to this, dislocation dynamics or not dislocation dynamics, this is how dislocation dynamics schematically is. You start with an atomic potential, you run MD simulations to make dislocations move, you quantify the motion, you import it into DD model, and you then run long and large DDD simulations to compute strength. This is the alternative that we started a while ago. You just skip it over. You start with interatomic potential, and you just run huge and long and compute the same strength. Okay, and in our context, with our resources, we can afford to do it in a relevant range. Okay, so that's one justification. But there is a benefits. Okay, well, MD is a very mature method. We don't really put any effort in developing it. DD is still under active development. So yeah, it's very expedient. takes much shorter time and lower cost to begin making predictions. I mean, if you, a graduate student, undergraduate student can set up some simulation in a few minutes and it will run. Okay, so it's very, in that sense, it's a human cost is much lower to run this simulation. Importantly, and again, I mentioned that we are very much concerned about prediction uncertainties at Lawrence Livermore and other labs, of course. It actually takes out in all upscaling uncertainties here, going from here to there. It just confines all uncertainties to one single source, interatomic potential. Mind you, there are serious uncertainties, but they were there anyway. So we kind of take out one source. That's good. And of course, it's very scalable. It can run huge simulations very nicely, much easier to scale up than dislocation dynamics in particular. Okay. And it has become a workhorse for predictions in the context I'm working on at Lawrence Livermore lab. But then the question begs, and I need to address this question because my manager are asking it. Is it really worth to continue developing DDD method? I started in 2000 and now I need to defend it, what's going on? Well, that's one justification. This is a side-by-side simulation. One was done with MD, another done with DD. They are initialized exactly the same way. Even the initial sources are the same, positioned and oriented and whatnot. And run side-by-side, they do the same thing. So they deform the box the same way and pretty much. So it looks like they're, doing the same thing. But it takes 1 million GPU hours to run an MD and about 20 hours to run in DD. So, you have still considerable savings, okay? And especially if you're interested in low training rates, MD still cannot reach this can. So it's a serious justification. However, we also found another interesting aspect of why you want to do both. This particular simulations, this is what they reproduce in terms of dislocation density. This is MD, green, and the blue is in DD, and they're very different. In DD, whereas in MD, dislocation density reaches stationary state, as I was previously describing, it never happens in DD for some reason. Dislocation density keeps increasing. When we look inside, we see very dense tangles of dislocation they form in DD. And they never do. They do form sometimes, but they find a way to dissolve themselves in MD. When we looked in more details and what's behind these behaviors, looked in MD, there is, again, we termed it sticky nodes. Some they develop in DD, but not in MD. What's going on? So it was worth looking into MD. What we're going to see is a simulation of a fragment of a dislocation network in FCC. And classically, these nodes can only move along the blue lines. You will see that something happens which was not known before. In fact, it was discovered a complete new mechanism of dislocation reaction where these nodes manage to move in 3 dimensions. What they do in MD and they never did it in DD. So this is the movie. If you watch at this corner, this is where this reaction will take place, I think, unless I'm forgetting. Yeah, it is. And then it will just find a way to move dislocations out of this lock somehow and resolve the whole damn thing configuration in MD. That's what it does. In DD, it never did. But we understood it from MD simulation and inserted this mechanism, this additional freedom into DD. And once we did, this is what happened. So the red line is DD simulation under exact same conditions, but with this additional sort of mechanism inserted in it. So it's very helpful, therefore, to run the simulation side by side. We call this practice cross-scale matching. They run on the same scales, they run exactly the same thing, and it is from the discrepancies between the two methods that you learn most. And so that's a lot of fun, and we work with that mostly with Nicola Burton at Lawrence Livermore. So cross-scale matching improves fidelity of dislocation dynamic simulations, right? So to continue with this, what are these very large MD simulations additionally good for? I probably will just take another 5 minutes or so. Are they just a computational engine to compute a number, or they are indeed fully resolved computational microscope? Ideally, this is what you'd like. There are probably lots of golden nuggets of knowledge and understanding hidden behind these huge simulations. But here lies the problem. This is about 70 years from first molecular dynamics simulations performed by, actually, it is incorrect name, sorry. This is actually Mary Mensai, I confused it. So Mary Mensai was the one who coded first dislocation dynamics, molecular dynamics code, and run the simulation. Who you see and who published the papers are Bernie Alder and Tom Wainwright. First paper came out in '56. And they, out of simulation, tiny simulations by any measures, in this period of time, I found something quite interesting. I mean, they watched this jiggles and wiggles all the time. From 64 atoms, they figured out the existence of melting transition, the two-dimensional hard disks. From 108, it's not 10 to the 8, it's 108 atoms. They actually figured out this long-tail hydrodynamic instabilities and the fluid flows, right? Now, what is that we're doing now? It's just insane. This simulation was completed, some numbers. Simulation was completed 2017, back then on Sequoia machine. It ran overall for about 20 days on full machine equivalent. It generated trajectory data that at that time was equal to about 10 times Google worldwide storage capacities, okay? So 10 Google's data. Only a tiny fraction, of course, could be saved. It took me 5 months to post-process it into dislocations. And when I looked at this humongous movie, I couldn't spot anything interesting. It was still so humongous that a human brain cannot see into it. So, I mean, this is ridiculous. Now, on El Cap, the same simulation would have taken 8 hours only. With the fastest fully parallel I/O, you can only save about that much fraction concurrently with the simulation, right? And if you do that, with under an hour, you will feel the whole humongous storage system of Lawrence Livermore, right? So if you just few snapshots that you're able to save, there is a, it will take hundreds of years to post-process with the current method. So it's just, mind-boggling. And this immense method, if you really use just the ways we handle data of the simulation right now, would not have yielded any important insights. We don't know what to look into. The amount of data is so overwhelming, it's just impossible. You see nothing when you see so much. All right, so is it really hopeless? And that's a quite subjective take on things, admittedly. At least in the context what the things we are doing, what we see is that evolution in time and space is highly intermittent. Things don't happen most of interest, don't happen most of the time in most of the places, right? So in material dynamics, it has to do with all kinds of behaviors, which I list here. Things like that happen in plasma space physics and fluid dynamics and so on. And my take on it, again, rather speculative and subjective, is that you only need to focus on these pivotal events. And most of the rest of the trajectory, because it's so huge, can be sort of not even looked into. But the point is that how do you extract these events? Now, in the simulation that I mentioned, 2017, I am certain that if we could process every snapshot, every time step, I could have distilled all the relevant information from that many exabytes, 10 Googles, remember, to under 1 terabyte. And I had no idea how to do it. Okay, so it's a huge reduction. There's not much information there. So it is, again, it's too general an observation that to make it general, is that essential data is of limited size. You really need to focus on this event. The rest of it is like, and it's only in these conditions when you need to collect statistically representative number of these pivotal events where you deserve to run these huge simulations, okay? Large enough and long enough to see, to evolve the system through possibly large, but finite number of statistically So sorry, pivotal events. Okay. So again, that's my take. And this is specs I would like to have on a desired data management pipeline that doesn't exist yet. So it has to be on the fly, and otherwise it will be indiscriminately lost. Hopefully, the cost of extracting these golden nuggets is not exceeding, although I am willing to negotiate with it. Sometimes it's actually good if your analysis tools are more expensive than your simulation itself, at least that. But this I would not negotiate on. I'd like to stay in the loop. I'd like to eventually distill this data extracted from these huge simulations into a form I, as a human, are able to comprehend. And I cannot comprehend many things. We are very weak in that sense. But I'd like to stay in the loop, sorry. To relegate everything to AI, it can handle it, but yeah. So with that, I show my summary. And I will also show one last slide after summary. So don't clap before. Okay. So, okay, direct MD simulations have reached, in certain contexts, sufficient efficiency that you can run large and long and actually gain direct access to all this data and compute things that you want to. This practice of exascale matching, actually, when you can run MD simulations and some mesoscopic simulations on the same scales, yields lots of interesting information, especially when they disagree clearly. And that is a big boo-boo. Our ability to generate data is far outpacing our ability to actually extract any knowledge from it. So that's, to me, is really exascale data bottleneck that somehow we need to deal with. And the last slide, this is just the things. If you want, I still have some free time this afternoon and possibly even tomorrow if you will to. These are things, iceberg means that what I described today is just a small part of what I do. I do other things as well. And these are the kind of the, topics I would be willing and to talk about and have something to say. And this is all, and thank you very much.
Vasily, it's a really thought-provoking, beautiful talk as always. I think the answer to your question, if I venture, is you need a large language model and vision language models. You basically, like you have been talking, very thought-provokingly for 50 minutes in English, and you're basically saying, what event in your 50 exabyte breaks Hertz and Loth and breaks your own picture of what dislocation rules are. So you need an engine that sort of can look at these movies and say, which one, does not fit Hertz and Loth's narrative.
You mean anomaly detection kind of?
Correct.
Yeah.
It's like you have to have like general cognition and pattern matching to know what's important. So I would just say it's clear that you need to work with large language model and vision language model, but perhaps tuned to dislocation corpus.
Yeah, we wrote a number of proposals to do just that, non-funded.
Great talk, Vasily. I haven't followed a lot of plasticity-related MD for many years, and the progress has been fantastic. So, you didn't say too much about polycrystals and things like, so I remember some of the big challenges at that time, right, was to do realistic, grain sizes and dislocation densities. And, I think dislocation pileups or grain boundaries were out of the question. The transition from whole pitch to grain boundary sliding was out of...
To inverse whole pitch,
Lots of things that were not available. I mean, and now it seems that it's all happened, which is great.
Yeah.
And maybe it's just the scalability, but I mean, the remaining thing seems to be like, the rates are still very high, right? I mean, 10 to the 4 is still very high. So, and I mean, isn't that like a huge source of uncertainty to compare to real materials also?
It certainly is. It certainly. I would say that it's time to answer or?
Yeah.
Okay. I'd like to first take on your real material last two words. For us, these rates and these materials are real.
Oh, yeah.
So that's a disclaimer. We actually are interested in precisely this range of straining rates. Yeah. What you mean by real is, of course, what everybody else cares about, right? And we cannot reach that with MD, obviously. I would put it that way. I mean, we're always sort of cognizant of this huge gap in the rates. Again, we only went down to 10 to 4, and even then barely. You need to go to 10 to -3, 10 to -4. That's still a huge gap. So that's why mesoscopic metal properly calibrated like DD will still play a major role. That's how I see it. Now, what is more surprising to me, I mean, it's true that it's a source of uncertainty and 10 orders of magnitude and rates and so on. Most surprising is how similar they behave at these high rates to what is observed at low rates. So it scales. At least so far what we see is that the physical mechanism involved at the very high rates and the low rates are precisely the same.
I have one more question. So, how did you guys GPUize and scale Paradise? Because, the non-local thing seems like a nightmare to
True.
make it. And I remember the scalability was an issue.
Yeah.
15 years ago.
Right. So, okay. So we do eventually engage MPI parallelization, and that is difficult. Turns out that presently available GPUs, like the ones on El Capitano or Talumnia, are so damn efficient that we can afford to run the whole damn DD simulation on a single node.
Oh, wow.
Okay. And that is ported very efficiently by Nikolai using this Cocos front-end, implementation that developed in Sandia. So it's all Cocosized.
Okay.
Yes.
Thank you for the presentation. I'm very curious because you had like avalanches and intermittent plasticity. Can you comment on experiences and challenges when the physics is truly multi-rate and multi-scale?
Yeah, we had our fun with this trying to detect and quantify avalanches. Very difficult, again, because they're extremely intermittent. They are there, we observe them, we can detect. We haven't moved enough along this line to quantify them, the spectrum, avalanche spectrum in particular, so on. You can kind of infer some of it from stress strain serrations. How large is the stress drop magnitude? What is the spectrum of this? That's typically what's done in crackling noise and other avalanche phenomena. We do that, that works, but we really, the focus was what's behind this drop? What is the event? And that we have moved along a little bit, but haven't really completed the picture yet. So it is very interesting indeed.
Thank you.
Yeah, so you have a very interesting slide about DDD and compared to direct MD approach. You mentioned that the only uncertainty source of uncertainty in the direct MD is the interatomic potential. So I wonder what IP, what potential do you use, and did you investigate some uncertainty in the potential model that you use?
Yeah, I think we have a time slot to talk.
Right.
Okay, so we can talk at some length because, in fact, last 3 years we had a very targeted project, where we developed what we call bespoke or potentials a la carte, in exactly the purpose to quantify and minimize uncertainty in their predictions. So to tell you, sometimes we run the same simulation 100 times at different iteratomic potentials, or we vary parameters of the potential. So there's a lot of work on that along this line going on, and indeed we are very concerned. It is, but it's nice, what my point was, it's good to have a single source, then you can focus on it.
Right.
And we are focusing on it at this point. So it's a little bit too long-winded to describe exactly what we do. But we use information matching methods like Fisher information to quantify and minimize uncertainty in interatomic potentials. Yeah.
Last question.
Thanks for the great talk. Could you go to slide 36, please? So it seems like, from what I understand, you've been able to do such incredible research by looking at the difference between direct atoms, all atom simulations, and then trying to see which features of those simulations aren't yet captured by smaller parameter-based methods. But I think for a lot of problems outside of this domain where we don't have the data and we don't have these all atom simulations, we kind of have to go the other way, where we have models for dynamics that we think through PDEs these systems should obey, and that we may be able to simulate on a smaller scale a small number of atoms. So I wanted to pick your brain on, let's say you have this kind of different series of length scales that different dynamics occur on. What tips do you have for a given problem of interest? And maybe you can take us through your process of thinking about dislocation dynamics. Let's say you have dynamics of interest, you have the ability to simulate maybe all atoms, but at a smaller length scale. How do you know which features of the data to build statistical approximations for to understand and integrate the dynamics of the system that you expect, but for less data?
Great question. Thank you. I have thought about it a lot. I don't know I have a good and ready answer to that. But my sense is that we need to invert the modeling hierarchy. We need to go top down. And from the top, you have a quantity of interest that you say, okay, I'd like to predict it, that thing. No, probably not more than that, or maybe a vector with this uncertainty. And then you work back to your model that you use for that prediction. What should be uncertainty in its parameters? And then if you need to go down, subscale simulation to quantify this uncertainty, you keep propagating it down and down and down over this hierarchy, but you go top to bottom. I think this is a more, how to say, engineering approach to quantifying uncertainty and making accurate predictions than what we engaged in. But historically, that was how it was. So you go from bottom. And that leaves uncertainty undefined in many senses, yes.
Thank you very much for a great talk.